Hi friends, welcome to the second MCQ video on the topic induction motors. So let us start with discussing the basic working principle. So in an induction motor we have a stator and a rotor. The stator of a three-phase induction motor is fed from three-phase AC supply, and this three-phase AC supply will set up a rotating magnetic field of this kind in the stator, and this will link with the rotor conductors, and this will induce an EMF in the rotor conductors according to electromagnetic induction, and this EMF will circulate a current in the rotor circuit if it is closed circuit. And according to Lenz's law, this current will try to oppose the cause, and in this case the cause is the rotating magnetic field in the stator. So the rotor also will try to rotate in the same direction as that of the rotating magnetic field, and it will try to attain the speed of the rotating magnetic field, which is known as the synchronous speed. So this will also try to rotate at the synchronous speed, but the rotor will never reach the synchronous speed, which will always run at a speed lesser than the synchronous speed. And the synchronous speed of a three-phase induction motor is given by ns equal to 120 f by p rpm, radians per minutes, where f is the supply frequency and p is the number of poles, and the rotor speed n is always less than the synchronous speed, and this difference in speed, that is ns minus n, or synchronous speed minus rotor speed, is called the slip speed, and this over ns is called the slip. So slip s is equal to ns minus n divided by ns. You can also represent it in percentage by multiplying it by 100. So these are the basic equation that we'll be using throughout this video. And these are the two constructions of rotor. One, it can be a squirrel cage type, or it can be a wound rotor or slip ring type. In squirrel cage we are having conductors as bars, and these are short circuited at the ends by end rings. But in the case of a slip ring or wound type rotor, the rotor is having the winding as same as that in the stator, and they are having slip rings on them through which we can connect external resistance also, and this is normally connected as star, and under normal running conditions it will be simply starred and the resistance will be cut out. So by adjusting this resistance we can increase the starting torque and all. Now the first question: a 6-pole 50 Hz 3-phase induction motor cannot run at a speed of dash rpm, 500, 750, 950, 1000, and here you go. And the answer is 1000, because we know that the synchronous speed n is equal to 120 f by p, and if you substitute it you will get the synchronous speed as 1000, and a rotor or motor cannot run at the synchronous speed, so it cannot run at 1000 rpm. The maximum possible speed of a squirrel cage motor running at a slip of 4% is dash rpm, 2880, 1440, 960, 1000. Here you go. And the answer is 2880. This you can simply obtain from the slip equation. We know that slip s equal to ns minus n by ns, or rearranging you can get n equal to ns minus s into ns. So simply by substituting you can get the answer. Now the next question: 4-pole 3-phase induction motor runs at 720 rpm. The slip being 4%, the frequency is 16 Hz, 25 Hz, 50 Hz, 60 Hz, and here you go. And the answer is 25 Hz. So first you have to calculate the synchronous speed ns by using the equation n by 1 minus s. Then once you have ns, you can use the equation ns equal to 120 f by p, and you will obtain the value as 25 Hz. Two of the three supply leads of a three-phase induction motor at a slip s are interchanged. Then the new value of slip is dash 2 plus s, 2 minus s, 1 plus s, 1 minus s, and here you go. And the answer is 2 minus s, because under normal condition slip is given by ns minus n by ns. Now if you interchange the two terminals, then the speed will be, or the direction of rotation will be reversed. So n will be minus n, and if you substitute and simplify, you will obtain the expression as 2 minus s. The speed of rotating field due to rotor current relative to rotor surface is ns, sns, n, 2n, and here you go. And the answer is SNS, because the speed of rotating field due to rotor current relative to the rotor surface is slip times synchronous speed, because rotor also is rotating, so it is the slip times synchronous speed. The speed of rotating field due to rotor current relative to the stator core is ns, n, sns, 2ns, and here you go. Yes, you guessed it right. The answer is ns, because the stator core is stationary and the rotating field is rotating in the synchronous speed. So the difference is ns. A 3-phase 400-volt 4-pole induction motor is fed from a 50 Hz supply mains. It runs at a speed of 1440 rpm. The rotor frequency is dash Hz, 2, 50, 48, 60. And here you go. And the answer is 2. Because the rotor frequency is given by slip times the actual frequency, the stator frequency. So here you have to find the slip value and you have to multiply it with the frequency and you will obtain it as 2. The pull-out torque of a normal squirrel cage induction motor usually occurs at a percentage slip of about 5 to 10, 20 to 25, 30 to 40, 40 to 50. And here you go. And the answer is 20 to 25. So the pull-out torque of a normal squirrel cage induction motors occurs at 20 to 25 percentage. The air gap between stator and rotor of a 3-phase induction motor ranges from 2 cm to 4 cm, 0.4 mm to 4 mm, 1 cm to 2 cm, 4 to 6 cm. And here you go. And the answer is 0.4 mm to 4 mm. So the air gap is normally 0.4 mm to 4 mm. When the rotor of a 3-phase induction motor is blocked, the slip is 0, 0.1, 0.5, 1. And here you go. And you guessed it right. The answer is 1, because we know that slip equal to ns minus n by ns. Under blocked condition, there will be no rotation, so n will be 0, so ns by ns equal to 1. The full load slip of a 3-phase induction motor ranges from 2% to 5%, 5% to 10%, 10% to 20%, 20% to 30%. And here you go. And the answer is normally the slip is in the range of 2 to 5%. Please remember. The rotor windings of a 3-phase wound rotor induction motor is generally dash connected: star, delta, partly star and partly delta, none of the above. And here you go. And that was a simple question. Normally the wound rotor is connected star in star, and I have shown it at the beginning of this video. A wound rotor motor is used in applications where high starting torque is required, speed control is required, less costly motor is not required, high rotor resistance is required during running. And here you go. And the answer is where high starting torque is required, because as I have already told, you can add external resistance at starting so that you can make the starting torque high. A 4-pole 50 Hz 3-phase induction motor operates at a slip of 5%. The frequency of the EMF induced in the rotor will be dash Hz: 2.5, 10, 25, 50. Here you go. And the answer is 2.5. And that was a simpler question, because the rotor frequency is equal to slip times the stator frequency, and the slip is also given and frequency is given 50 Hz. Slip here you have to take it as 0.05. Actually it is given in percentage, but in calculating the frequency you have to use it as 0.05. That is the only thing you have to remember. The rotor current in a three-phase induction motor is dash the slip, inversely proportional to, directly proportional to, independent of, twice. Here you go. And the answer is directly proportional to. So rotor current in three-phase induction motor is actually directly proportional to the slip. If the slip of a three-phase induction motor increases, the power factor of the rotor circuit is increased, is decreased, remains unchanged, none of the above. And here you go. And the answer is decrease. So they are having inverse relation. The starting torque of a three-phase induction motor is dash the supply voltage, independent of, directly proportional to, square of, inversely proportional to, and here you go. And the answer is directly proportional to the square of supply voltage. Starting torque is directly proportional to the square of supply voltage, as it is directly proportional to the square of current, and the current in turn proportional to the voltage, it is directly proportional to the square of voltage. The maximum torque of a three-phase induction motor under running condition is inversely proportional to supply voltage, inversely proportional to the rotor reactance at standstill, directly proportional to rotor resistance, none of the above. Here you go. And the answer is inversely proportional to the rotor reactance at standstill. At no load, the rotor core loss of a three-phase induction motor is large, small, practically zero, none of the above. Here you go. And the answer is practically zero. So at no load, the core loss is practically zero. If a three-phase induction motor is running at a slip of S, then approximate efficiency of the motor is S, 1 minus S, 1 plus S, S minus 1. And here you go. And the answer is 1 minus S. The efficiency can be approximately said to be equal to 1 minus the slip. For higher efficiency of a three-phase induction motor, the slip should be large, as small as possible, very large, 1. And here you go. And the answer is very simple. It should be as small as possible, because the efficiency can be equal to 1 minus S. So slip is small means efficiency is high. The approximate efficiency of a three-phase 50 Hz 4-pole induction motor running at 1350 RPM is dash percentage, 40, 50, 65, 90. And here you go. And the answer is 90. Here you have to find out the slip using ns minus nr by ns, and the efficiency is 1 minus s. You have in a squirrel cage motor, the number of stator slots is dash rotor slots, always equal to the number of, always greater than the number of, always less than the number of, either more or less than the number of. And here you go. And the answer is either more or less than the number of. So they should not be equal to avoid the magnetic locking. If the air gap between the stator and rotor of a three-phase induction motor is increased, then no load current is decreased, leakage reactances are decreased, leakage reactances are increased, none of the above. And here you go. And the answer is leakage reactance are increased with the increase in air gap. In a squirrel cage induction motor, the number of rotor bars is generally an even number equal to the number of stator poles, prime number twice the number of stator poles. And here you go. And the answer is prime number. In a squirrel cage induction motor, number of rotor bars is generally taken as prime number. And that is all for this video. If you like this video, please do like, share and subscribe. And if you have anything to comment, please use the comment section. You can also ask questions or doubts in the comment section, and you can suggest topics also in the comment section. Thank you.